So we have the first talk is from Lortek. It's a combined talk between Ramon Moreno and Ander Muniategui, and it will be about deep learning on industrial quality control, radial welding, and active thermography. So our two speakers here will be, on the one hand, Ramon Moreno, who is engineering computer science, is a PhD at the university in the Basque Country, and he is a specialist in artificial intelligence. He's been working in research during many years, having publications in the international ranked journals, and he's been working in many different countries like France, Brazil, also in Spain, and also in industry, like in automotive, in Big Connect, and nowadays he is Lortek, senior researcher in the area of Industry 4.0. And on the other hand, Ander Muniategui is also a PhD in biomedical engineering, and he has a double bachelor in industrial engineering and materials engineering and physics. So he has participated in many different projects with a focus on data science for biotechnology, aeronautics, and material processing. And now he is working in the control and evaluation area of Lortek in the development of algorithms for the analysis of image processing in real time of big data, obtaining all the productive lines that make use of the welding processes. So I give you both the role of presenter, Ramon and Ander, so you can now share your presentation and to hear about it. So thank you very much.
Okay, thank you very much for this nice introduction. We also should say that together with us is Eider Gorostegui, who is our specialist in thermography. And we are going to start with what is this one? Okay, everybody can see now the main screen.
Yes, I can see clearly.
Okay. Well, here we are going to explain the two cases of use of deep learning for industrial environments. The first one is for crack detection on active thermography, and the second one is for quality control in welding processes. Okay. Lortek is a research center located in the north side of Spain, and we are specialized in metal, welding, laser joining processes, and that's why we are very linked to industry, and we have a small area specialized on data, computer vision, non-destructive techniques, process analysis, monitoring, and so on. And in this area is when we have done this the work that we are going to explain first is for cut detections and active thermography. In the introduction, first we are with an overall introduction about what is thermography that Eider Gorostegui is going to explain you the context. After that, we are going to show the experimental measurements. We are going to explain the setup, how we have faced this problem. We have used also a retinopathy in order to solve this industrial problem. Finally, we are going to show the convolutional neural network and their experiments and the conclusions and with the results. So I'll give the word to Eider, who is going to explain you what is thermography.
Good morning, everybody. Well, I will begin with a little introduction that explains why we use active thermography for defect detections in the industry. Traditional and non-destructive test inspections in industry are based usually on manual techniques like magnetic particles or dye-penetrant testing techniques that cannot be automated. And what we want is this automatization. They are dirty, they are time-consuming, and they are user criteria dependent. This is why here we want to introduce algorithms which will help us to quit this subjectiveness in the measurement. No? So active thermography substitutes these traditional inspection methods, reduces inspection times, provides clean and contactless inspections, and assures repetitivity in the measurements. And so what we do, we need thermography. What does it give us? It consists on hitting a sample, and when you hit a sample and you have a defect on this sample, heat propagation is affected when a defect appears. So we capture this heat using a thermal camera, and we process those images in a computer in order to detect defects automatically. We can have several excitation sources, air, laser, or induction, for example. And in this work, we are going, the images you are going to see, or thermograms, are correspond to induction thermography. But you have to keep in mind that the main objective of this work is to present the developed automated detection algorithm, which will give us the plus with respect to the traditional industrial inspection methods. So we have used a 3D infrared cooler thermal camera and a 3 kilowatt inductor generator, and the samples we have inspected are the ones you see on the screen. And the inductors employed are also shown on the right side of the screen. The usual setup is the following. You have the camera and inductor situated in a certain place to inspect an area, and a controller, you can see here, is the one who gives the start to the heat impulse and the start of the recording. In this way, we record both the heating and the cooling of the sample, and we store all this information in the computer. It is then when you process those images and you perform the automatic defect detection. What we have done at Lortek is to give Ramon's team all the experimental measurements we have performed on the laboratory. So this is the setup, and here you have to focus on here. This is slide is very important because our inductors are orientation dependent. This means that for each sample we have to perform more than one measurement. So for each sample they will have 4 images. Because in this way we are sure that we are going to detect all the cracks on a sample, because we assume that cracks can grow at any direction. This is an example of 4 measurements on the same sample with inductors at different orientations, theta equal to 0, 45, 19, and 135. And as you see, I have highlighted the areas which are most heated for each configuration. So, with all this information, right now, Ramon is going to explain you how he has processed these images in order to obtain the defects that appear here.
This is the part of the thermography sensing. Now we collect the data, and we are going to use the data in order to provide a solution. The scheme is in these 3 blocks. Thermographical sensing. After that, we are going to apply a scene reconstruction, and finally, the scene segmentation. In this work, we are talking about the scene in a state of images, because from these 4 images, we make a reconstruction, and this image, the right one image, summarize the scene taken by the left 4 images. We are going to work with the right one. That is the summary of the scene. Here we have a small problem, is that to collect this kind of images is difficult, and we have a few images with cracks in order to develop a ground truth big database in order to train a deep learning model. As is well known, in order to train deep learning models, it is necessary to have a lot of images, and in this case we have 10 or 15 thermographical collections. So in order to overcome this problem, we have used retinopathy images coming from retinopathy, and these 4 databases are available in the internet, and these are the kind of images, the retinopathy images. The ground truth is the vessels, and fortunately the shapes of the vessels are similar to the cracks. So we have used this collection of images in order to train our model. Putting all together, all images in this database, we have about 100 images. It's not enough, but using oversampling, we have got up to 1,000. In order to train the image, we have used the BGG model. Is well known. It's on the state of the art. It's fast, and is easy to understand. It has few layers, and the best thing have this convolutional neural network is that this network has been trained with using some million of images, and the resulting model are available for everybody in the internet. So we have used this network, some layers, and we have used the training weights. So here we have transfer learning. And we are going to use this network in order to train our database using the retinopathy images. The BGG network, we have made some changes. We have used the output of the ReLU 1.2, ReLU 2.2, and ReLU 3.3, and we have connected all of them by concatenation, and after that, convolution and the softmax function. So, from the original BGG network, we have transformed it into a residual network. And the training is very fast. And when one can see this graph of the training process, we can see that the accuracy is very good at the first stage, but this is because we have used the weight of the previous model available on the internet. And after this process, we train this model using about 1,000 images of the retropital images, and the output is our model. And this model we have used it in order to make a segmentation using the summary image. In these results, this is the left one is an example of a thermal image. The middle image are the summary image using the 4 collected images, and on the right one we have some output of the segmentation. According with our researchers, the output is very good, and all the class on these weldings are detected, except in the last one that we have some false positives. So this is more or less our work at this moment. We have made transfer learning using the model available on the internet, using the weights, and we have used also a data set of images, retinopathy images, in order to train our model. And finally, because of the similarity of the vessel shapes with the class, we have tested the resulting model with our graphical images, and the results look good enough. As further work, of course, we want to make our own database using an electron microscope that we have in our building, and make a good collection of images in order to train again similar network, and we expect, of course, to have better results. And this is our first work, and the second work that is related with quality control on weldings, radial weldings, is going to be presented for Ander Muniategui, and now I give you the word, Ander.
Thank you, Roman. This part corresponds to another example of deep learning application in an industrial welding quality control of welded parts. Here, the main objectives have been to create a database so that can be used in deep learning model training. And the objective of this work has been the development of an artificial vision-based system for the identification of defective parts on welds of safety components for capital goods. It was implanted in a real productive line, and it required the design of illumination system, set the connections to the automaton to discard defective parts, create the required interfaces for visualization, and to create a balanced database for deep learning models. The welding under study joins 2 cylinders together. One cylinder is introduced inside the other, and the boundary region is welded by adding material. In the productive line, one part is welded every 2 seconds, and the size of the regions to weld is approximately of 2 to 3 millimeters. These effects are known as lack of fusion since they show a not welded region. This means that there is a region without added material. Initially, the quality control was carried out by qualified operators via visual inspection, and the observed defective rate was close to 1%. The aim of the project consisted on the development of the hardware and software so that when implanted into the productive line, it could discard defective parts in an automatic way. The development of the inspection system was carried out in 4 phases. In the first phase, the setup was designed. Since the region to be inspected had circular shape, 3 cameras were placed at the same distance from the center of the circle and at 120 degrees from each other. In order to amplify the region to be inspected, 3 telecentric lenses were used. And for illumination, a spherical dome and an illumination system were used. Due to this setup, it was assumed that the images obtained from any of the cameras would be very similar, and hence it was considered that the same software could be used for the analysis of the 3 images captured from the 3 cameras. Each inspected part was afterwards classified as defective or correct by combining the 3 outputs. Initially, grayscale cameras were used. Within the obtained images, the lack of fusion regions could be identified easily, as can be observed in the regions pointed by the red arrows in the images on the right. An initial software for grayscale image analysis was developed. The aim of this software was to detect the characteristic circular boundaries of non-welded regions. A preliminary proof of concept showed that the results of the algorithms were promising. However, in order to move to the productive line as fast as possible, we decided to simplify the image analysis step by adjusting color cameras so that the material added within the welded regions could be observed with a different color. This way, the welded region could be easily identified by segmenting the image from color data. The new color-based algorithm was developed and implanted in the productive line. After a week of data acquisition, the feasibility of the algorithm was determined. Results showed false negatives and true positive rate above 94%. With the results, it was decided to set the algorithm in the productive line and to activate the automatic discarding of inspected parts. The aim was partly to do a sinusoidal classification of images so that the time required to create a database for deep learning models training could be reduced considerably. With the aim of ensuring previous results, 6 months later, the data captured from the inspection system was retrieved and analyzed. During this time, the algorithm inspected nearly 1.5 million of parts, from which 25,000 were discarded as defectives. These were visually inspected one by one and to determine the final feasibility of the algorithm. And finally, a balanced database of defective and correct parts was created. This was used to train deep learning models. One of our first attempts with this database consisted of accommodating the previously developed algorithm for grayscale images into well-known LeNet and AlexNet nets as processing steps. And as indicated before, this algorithm aimed at searching the characteristic circular boundaries of not welded regions. For this, 2 types of filters were used. The first one was a one-dimensional polar discrete Fourier transform-based filters, and the others were tailored Gable filters. In the figure of this slide, each row corresponds to a different image associated to different inspected regions. In columns, the output of the different steps of the algorithms are shown. First, the borders of the input images are determined. Then, wave-like patterns are obtained nearby circular boundaries, and finally, these wave-like patterns are used to highlight circular shaped boundaries observed in defective parts. Thus, are this one and this one. The boundaries and wave-like patterns are obtained using one-dimensional polar discrete Fourier transform filters. The aim of these filters is to find periodical patterns in images. In fact, a specific coefficient associated to a desired frequency value of an expected square signal is determined by using discrete Fourier transform. This is carried out using convolution of Taylor filters. Square signals are characteristic of boundary regions, and this way, these filters can be used to find boundaries from images. These are the boundaries of these images. Furthermore, a filter bank of these types of filters can be used to obtain a wave-like pattern by applying them sequentially. Wave-like patterns are only obtained in case input images show circular borders. Since the desired output is to only highlight circular boundaries, these wave-like patterns must be identified and transformed to boundaries. For that aim, Taylor-Gabor filters banks have been used. When convolved with images with wave-like patterns and summarized all the outputs by taking the mean by pixel, the expected highlighted boundary is obtained. These are the results of applying discrete Fourier transform filters, and these are the outputs by obtaining Gabor filters. And this is the final output in where the boundaries are highlighted. And in these slides, the output of different steps are shown for 3 images. And observe that the wave-like patterns are only found nearby circular boundaries. These are the wave-like patterns and are only observed in those boundaries or in the regions that there are this type of circular boundaries. Here also, you can find the wave-like patterns only in this type of boundaries. And here that there is no like fusion, there is no wave-like pattern. And the output of Gabor filter banks show a common region that allows highlighting the circular boundaries. These are the outputs of Gabor filters, and there are common regions that are associated with a region that corresponds to the lack of fusion. Here there are the outputs of these Gabor filters, and only in these regions there are some common regions associated with the circular shapes. And here these are the outputs of Gabor filters, and there is no common region, and thus the output doesn't show any highlighted region. The output is blurred. Since the structure of the developed algorithm follows a cascade of convolutions, accommodating it to convolution layers was done almost in a straightforward way. These layers were then introduced as preprocessing steps into LeNet and AlexNet nets. And both these modified nets and the original LeNet and Alex nets were trained and the results compared. The aim was to decipher whether adding preprocessing steps improved the results. The training was carried out using the images captured from one of the cameras, and in this case was camera 1, and they were tested on images of cameras 2 and 3. The results showed that preprocessing steps add relevant information to deep learning nets, since the obtained precision accuracy values for both cameras were higher than LeNet and AlexNet nets alone. Even though these are preliminary results, they seem encouraging. In conclusion, during this project, an inspection system has been developed and implanted in a productive process for the quality control of welded parts. The system has very few false negatives and few false positives, allowed to create a balanced database for training deep learning models. And even though the results shown are preliminary, they seem good and encourage us to continue working with deep processing steps and deep learning nets. That's all for my part. If you have any questions.
Okay, so thank you very much to the 3 of you for this very interesting talk. There's a question by Ismael Sanchez to Ramon, which is, why did you decide to use thermography as opposed to ultrasounds in order to detect the defects? Why this technique instead of the other one?
So using what we use the thermography instead of
ultrasounds.
Yes.
Thermography is for superficial defects. Ultrasounds is more for volumetric defectology. And in this case, we are interested in developing algorithms for superficial defects in general. Welding defects, they can be welding defects or other superficial defects or related to the manufactured part.
Okay, and how difficult do you think it would be to extend your algorithms in 2D, as you have it right now, as an image, to a volumetric prediction?
The point is that the technology, in the case of metals, is not valid for volumetric defects. We can have detection of some, maybe at 1 millimeter in depth, but not more. If you, on the other hand, go to composites, there we could perform volumetric inspection because conduction in these materials is different, so we can perform thermography both in superficial and subsuperficial level. But in metals, volumetric inspection using thermography is not nowadays possible.
Yeah. On the other hand, with respect to your first question, why we have preferred to use thermography in spite of ultrasounds is because we can use thermography without direct contact. That at this moment, in order to work with ultrasound, it's necessary to use direct contact. The technology is different. If we want to use ultrasonic thermography, this is a technology that nowadays is very, very soon. We need more time in front in order to work with this kind of technologies.
Okay, so regarding to this, Ismail has a second question, which is if these cracks are superficial or not. Because if they are, maybe it's not enough with a single image.
Thank you for your question, because this question is interesting. One of the advantages, in fact, of thermography is with thermography and directional induction, we can detect not superficial cracks.
Yes, they are.
Okay.
Yes.
They are all superficial. We can detect all superficial cracks.
Yes, of course, superficial or not superficial. This is one of the advantages of using thermography.
Because this non-superficial.
Before, I mean, they have to be superficial. We are not going to go through down to the volume. It can happen that what we see is a crack that you cannot see with vision. I mean, what we have checked, and if you want, I can send you later a slide. If you compare a macrography of the weldings you have seen, and you compare it with a thermogram, saying which is the exact dimension in the macrography is more difficult rather than in the thermography, because establishing the limit is more complicated visually. The heating helps you to have more contrast and really enhance the crack. In using vision, it's more complicated. I can say you later a slide so that you can see properly what I mean with that. And we in fact we are using macrography, and we are even going to SEM in order to check the real dimension of cracks in order to complete our model so that it can give us both the detection and the dimensioning and the orientation of the crack. For this reason, we are comparing all the time our thermography with vision, but not with other non-destructive techniques.
Okay, so maybe I can put you together in contact later, and you can further discuss if you have some more questions. Or okay.
Yes.
Very nice. So I had also one more question, which is for Adner. So he said one of the main reasons of doing all this research was also to generate like a database, right, for deep learning, which you couldn't find in the internet. So how are your plans to share this database, and how you share it? Because I don't think it's always easy to do it in the context of in an industrial context, right?
No, it's not easy to do it in an industrial context because we have to capture a lot of information, a lot of images. And it's difficult to extrapolate to other similar industrial applications.
Okay.
But what we need is to have a database that we could use for similar application we have in Lortek, because we are centered on welding, and many times the type of defects we have are very, very similar. So and we have different databases we can use afterwards, transfer learning for different new process analysis that are similar.
Do you think that one of the keys of all this new field of deep learning and data, big data, and in the industrial sector will be also to generate all these databases and to have the best possible database? It will be like a very relevant know-how at each company.
Yes, we think that if we have a good database of type of weldings and defects and type of nets that we can use to deal with those type of defects or identification, it will be easier for us.
Yeah, on the other hand, to use deep learning facing this kind of problems is very useful, because now there are new techniques like long short-term memories, generative models, and all of them are addressed to keep the previous knowledge. So we, for industrial problems, we have a lot of expectations with deep learning, because we can transfer our problems for lack of fusions, forest detection, quality control, train these models with some machines and use these same models with these weights to other problems.
Okay.
Yeah.
So thank you very much for your presentation and for the talk. I think it's time to move to the next one. So thank you very much again.
Thank you very much. Thank you to you for giving us this opportunity.
Thank you.
Yeah.